Hi, my name is Nathan. I did the server and UI code.
Hi, my name is Travis. I worked on the Wi-Flies and the automated rover.
Hi, my name is Jesse, and I worked with the user rover.
Hi, my name is Jake, and I worked on the IR sensors.
And we're Team 7, the
Racing
Rovers.
Our purpose of our project was to create a red light, green light with two rovers, one of them being automated and the other one being human controlled. Both of them get their signals from a UI that is built from Python. They both get their commands from that UI. The UI has a stoplight that changes from green to red that controls the automated rover. And then the human controlled rover has a button on the UI that controls whenever it moves. Whenever movement is detected on a red light, the rover that moved during that red light will be sent back to start. Also, whenever a game is finished, both rovers will be sent back to start just to make it easier for the next game to be played. If the human-controlled rover wins, that time will be stored on a Mongo database that can then be viewed on the UI as well. However, if the automated rover wins, that time is just discarded and thrown away.
Right, so my portion of the project was the IR sensors, which I like to think is the backbone of the of our project. So the design was there's two sensors for each pick on each side of our rovers here. As you can see, there's two lanes, and each side has two picks on each side. One for the goal, one for the distance. So the goal would work is when the rover passes through the plane on the inside, it would trigger and send a character to the server, which would denote a goal. And then the other one would work, it would sense the rover coming through, and it would pick up the change between the distance, and that would decide if it had moved a lot or moved a little or moved at all. So as for the code, I used analog to digital conversion, or ADC, to get the data from the IR sensors. And the way it worked is when data filled up the buffer in the PIC32, it would generate an interrupt, and that would send the data using a message queue to the main task. And after a fourth of a second, the main task would then get that data and compare it to the last data that it got. And if there's a large enough change, about 3 centimeters or more, then the rover would send a character to the server saying that the rover had moved forward, or if it decided that it had passed the goal line, it would send the character to the server saying that it had passed the goal.
Deal with the rovers was making sure they could send and receive simple data so that we could control them. So I, being the resident Wi-Fi expert for this project, figured out how we could reprogram them to connect to parent Wi-Fi to send and receive commands. After we reprogrammed the Wi-Fis, we had to set up the UART send and receive on a PIC32, so we got that to work, and then we hooked up the Wi-Fi to one of the Wi-Fi shields that we were provided, and hooked that up to the PIC32s, and it was a simple matter of sending and receiving data. The next step was hooking up the motor encoders to the PIC32s as well. So I went through and looked at the data sheets and figured out which pins we had to hook up to the motor shield that were provided to the actual motor encoders.
Afterwards, after all the motors are both hooked up to the PIC32, the next step was getting the motors to run and driving them using pulse width modulation, which drives off the duty cycle of a wave that is being produced. And so the way pulse width modulation works is during a period, the pulse will be a certain will be high at a certain amount of time, and by controlling like how long that is high will determine like when the motors will drive and like how fast they'll drive. So if it's at least 50% duty cycle, then the motors will go. And for us, we pretty much kept it almost about 95% of a duty cycle to keep them going as fast as they could.
Back into what we did in the beginning with connecting the Wi-Fis and sending specific data Once we got the motors to go forward, the next step was for them to be able to start and stop upon a command. So for this, it was pretty simple. We created a UART ISR, so every time we received a command through the UART module that was a specific command that we wanted, for example, red light or green light, whenever you received a red light command, you simply set the PWM to 0 and the rovers would stop. Whenever we received a green light through the UART, so therefore through the Wi-Fi's, then we would send the max or the 95% duty cycle to the PWMs, and they would start going forward again.
So after we were able to get like a simple like stopping and go command, the next step was really getting the rovers to flip directions and like go reverse. And to do that, it was simply like looking through the data sheets of especially the motor shield, which is what the motor's hooked up to, figuring out what pin controlled what the direction of each motor, and then from there figuring out how it connected to the PIC and like driving those pins high to or low to like reverse the direction. And afterwards, we had to
Read.
Okay. After going backwards, we intended to also go back to the start. So the next step was reading the encoder values. So for the encoders for the motors, they would like produce like a little tick every time the motors like reach a certain point in the revolution. So in order to do that, we had to hook up the encoder output out into a timer, which acted as a counter to keep track of that the ticks.
So once we got the data through the external timer that was driven by the pin, we were able to collect the value that was in the counter, in the timer, the counter value inside the timer, to figure out how many cycles, or how far the rover had gone forward. So we set up a reverse state in our state machine that would collect how far it had gone, reverse the direction of the motors, and send it back until it reached the same distance. This would drive the rovers back to start within about roughly an inch of distance, give or take, depending on the trial. The next thing we encountered was sort of a time delay.
And with that, we noticed with the way the code was set up at that point in time, there was a delay between receiving the commands and actually executing the commands, which was about a 3-second delay, which was too long of a time. So to fix that, we decided to change have the motors change from like the actual changing of the PWM duty cycle in the interrupt handler, while still maintaining the state machine separate from that.
So after this, we sort of deemed that the rovers were ready to be integrated with the other parts. And when we did that, we noticed that even with a very, very fast user, it was almost impossible for the user to maintain the start and stop pace as the automated rover, because it would be sent automatically as soon as the green light changed. So we decided that we would slow down the automated rover's speed so that the user would have a chance at beating the rover. So we slowed it down a decent amount so that given they were just straight green lights and the user was able to start and stop at a reasonable time, they should win the race every single time.
As for the UI and the server code for our project, the UI is coded in Python and it uses Qt as well, PyQt to be exact. PyQt is a library that has a lot of UI functions that you can utilize in order to create a working UI in Python. I also used Qt Designer in order to actually design the UI screens themselves, because it's a lot easier to use that as a drag and drop interface as opposed to actually coding the screens and how they look. the server code is basically embedded inside of the UI itself. The UI is running the server code. The server code is using sockets between the Wi-Fi's on the sensor devices, the sensor picks, and the Wi-Fi's on the rovers. The sensor picks are controlled via 2 threads that we have on the actual UI device, which is a laptop for us, which is running those 2 threads concurrently along with the UI, because if you do not have them running concurrently with the UI will freeze up and cause issues for the game. While the rover sockets are connected via just straight up sockets, they're not on separate threads, they run along with the game itself. As for a demo for the UI itself, as you can see, this is the main screen of the UI. The UI's main screen has 2 buttons, a new game button and a scoreboard button. When you click the new game button, it will take you to the game screen itself and play a sound. The main screen, as soon as it appears, starts a timer at the very top in seconds, milliseconds, and minutes. As you can see, it also has the stop light and the go stop button. The go stop button, whenever it is pressed, changes its state from stop to go. The stop light also changes on a timer. It has every 5 seconds it has a randomized chance of changing between green or red, and that green or red state will then control the automated rover. The button itself, the green go stop button, will control the human controlled rover. As for the scoreboard, whenever you click the scoreboard button from the main screen, it'll take you to the top winning results of the human controlled rover. The auto controlled rover, if it wins, those are just thrown out and aren't placed into the PyMongo database. This is just, all it does is just store the human controlled rover fastest times.
So looking back at our project, there's a couple improvements or changes we'd like to make if we had time. So for me personally, since I did the IR sensors, I would have spent more time researching different sensors for our project, because the ones that we were using weren't well suited for our task, and it made it very difficult to pick up the rover, especially when it's moving, because the sensors would see behind the rover, it would bounce off parts of the course, give a lot of data that we couldn't use, so it made it a lot tougher to sense the rovers when they're moving. The other thing I'd like to improve is the course. We built it using some cardboard blocks that were around the lab. If we had more time, we probably could have used some wood. And the reason that there's these front panels, as you saw in the demo, in front of the rovers, is because the sensor would see behind them, and we needed a flat white surface to bounce the IR off of. So again, improved sensors would have been very nice.
When it came to the rovers, I would have liked to improve the how straight the rovers were, because even though we adjusted one side of the rover as opposed to the other, it still like veered off a little bit. So if we had like a line sensor, you know, have it follow a line to go straight, that would have been nice. Also, it would have been nice to decrease or entirely eliminate the extra distance when it went back to the starting position, because almost every time the rovers would go back about an inch or so, an inch at max, past the starting position.
2 ideas I thought that would be cool to add to the game would be more to expand on the gaming experience necessarily than just the rovers. The first would be adding physical lights to the course so that the user could spend more time looking at the rovers actually racing, as opposed to the UI. Would have been as simple as setting up another pick with the lights and sending a signal to turn the light from green to red when that happened. And also adding levels of difficulty to the rovers, so we could make the automated rover go slightly faster or slightly slower based on, you know, easy, medium, or fast difficulty level.
As for the UI and the server, I would have made the actual device that has the UI running on it the Raspberry Pi with the touchscreen to make it more game-like and make it seem more like a game controller as opposed to a laptop that's just running the UI on it and is controlled by the laptop. Also, writing the UI in C instead of Python could have helped make it integrating with the other portions of the code, a lot easier because all the other portions were written in C, and integrating Python to C can kind of cause some issues there.